collecting telemetry is only the starting point. The real question is, can your team tell when users are struggling, costs are drifting, or quality is degrading? In this topic, we'll turn LLM signals into dashboards, alerts, and SLOs that drive action. Let's connect this to the work so far. We began by diagnosing why LLM applications fail in production: cost, latency, timeouts, OMIs, cascading failures, and drift. Then we designed a controlled inference platform and added reliability patterns. Now that OpenTelemetry is in place, the next step is to turn raw signals into dashboards, alerts, and SLOs that operators can trust. In LLM platforms, up does not always mean healthy. Users may still experience timeouts, rising token costs, weak answers, or constant fallback to another model. Dashboards bring these signals together so teams can see the full operating picture across the app: inference stack, GPUs, model behavior, and cost. SLOs turn expectations into commitments: response time, cost control, and quality targets. The key is to alert on symptoms that matter to users or the business, not every noisy metric change underneath. Good observability follows the request through the whole platform. From the user call, through the application, cache, router, model server, GPU, and any fallback provider, each stage should emit traces, logs, metrics, and events. Correlation is what makes those signals useful. Request IDs, tenant IDs, model IDs, routing decisions, and prompt versions tie the story together. From there, dashboards can separate service health, inference health, GPU saturation, model quality, and cost. OpenTelemetry acts as the connective tissue, turning scattered telemetry into one operational picture. Think of the core reliability dashboard as your service health baseline. It should answer the first incident question quickly: are users getting successful responses within the time we promised? To do that, separate traffic by endpoint, tenant, route, priority, and model family, because failures rarely hit everything evenly. Track latency with P50, P95, and P99, not just averages. Watch timeouts, errors, retries, and circuit breakers as symptoms of instability. Then add queue depth, wait time, concurrency, and saturation, which warn you when overload is building before users experience a complete outage. LAM latency is rarely average-shaped. It is long-tailed. Most requests finish quickly, while a smaller set gets dramatically slower. P50 shows the median experience, which is useful for spotting broad baseline shifts. But P50 can look healthy while many users are still suffering. P95 is often the better service level target because it captures recurring user pain. P99 is your tail alarm. It can reveal queuing cold starts, long prompts, fallback providers, or GPU contention. Always segment percentiles by route, model, tenant, prompt length, cache hit status, and priority. Otherwise, one blended number can hide the exact path causing the slowdown. LLM serving rarely moves from healthy to down in one step. It usually enters a danger zone first. Queues grow, wait time rises, batches fill, and GPU memory or compute approaches saturation. Queue depth tells you work is piling up, but wait time tells you what users actually feel. Watch saturation at every handoff: workers, routers, scheduler queues, model servers, and GPUs. When demand exceeds safe capacity, rejection should be intentional. Lower priority traffic should be shed first, with clear metrics by priority class. Controlled rejection protects the system. Silent timeouts are uncontrolled failure, and they deserve separate alarms. For LLM systems, tokens are the basic unit behind both performance and spend. A useful dashboard separates input tokens from output tokens, then breaks them down by endpoint, tenant, model, and route. That makes it easier to spot prompt bloat, unusually long completions, or a retrieval change that suddenly adds context. When latency rises or GPU usage spikes, token percentiles often explain why. Comparing expected versus actual usage also helps catch template changes before they become cost surprises. Semantic caching and routing are powerful cost controls, but only if you can see how they behave. Track cache hit rate by endpoint, tenant, embedding model, threshold, and request type, because one weak segment can hide inside a healthy average. Watch route mix to confirm traffic is flowing through the intended balance of local models, larger models, premium APIs, and fallbacks. Treat fallback rate as both an availability signal and a cost warning. If cache hits suddenly drop or fallback spike, investigate deployments, prompt changes, embedding drift, or model instability. Model reliability needs to be measured at the model version level, not only at the application level. A timeout spike in one quantized variant means something very different from malformed JSON across every provider. Track errors, refusals, validation failures, and fallback triggers separately for each model, route, tenant, prompt template, and traffic class. That segmentation tells you whether the platform is unhealthy, a provider is degrading, or one fine-tune is drifting. The goal is fast isolation. Identify the failing model, understand the failure pattern, and route traffic safely while the team investigates. When you self-host inference, the model is only one part of reliability. The serving layer can fail because GPUs are saturated, memory is fragmented, requests are queuing, or replicas are restarting. Start with GPU utilization and memory pressure, especially OOM events. Then connect those signals to LLM metrics, tokens per second, active and waiting requests, batch size, and scheduler queue time. Correlation is the key. If latency rises with long prompts and a growing queue, you likely have a scheduling or capacity issue. If throughput drops during restarts or OOM kills, you are looking at an infrastructure stability issue. Good SLOs translate reliability into promises users can feel. Start with user-facing signals. Did the request succeed? Was it fast enough? Did it time out? And was the response valid? Then add LLM-specific signals, such as fallback usage, cache performance, schema validity, quality gate pass rate, and cost per successful request. Avoid one global target. Segment by traffic class, because an interactive premium chat has different expectations than a batch workflow or internal tool. Finally, connect SLOs to error budgets. When the budget burns too fast, teams can slow releases, adjust fallbacks, scale capacity, or invest in reliability. Alert design should start with symptoms, because humans should be interrupted only when action is needed. A single CPU spike or latency blip is usually not enough. Prefer SLO burn rate alerts that show users are consuming error budget too quickly. Then add platform-specific signals, fallback rates climbing, caches collapsing, timeout surges, unexpected spend, or quality regression. Severity should match the response. Page for urgent user impact. Create a ticket for slower degradation. Annotate dashboards for context-only events. Every alert should also say who and what is affected: tenant, model, route, region, version, and likely blast radius. Advanced alerting is about correlation, not noise. A burn rate alert can catch both a sudden outage and a slow error budget leak. Cost alerts should ask, is spend high for this traffic, route mix, and baseline? Now imagine a prompt template deploy breaks cache keys. Cache hit rate drops, token volume doubles, latency rises, and fallbacks increase. A good system connects those signals and fires one meaningful incident: detection, diagnosis, mitigation. Quality alerts add another layer through eval failures, validation errors, user feedback, and drift signals. The goal is early warning that points engineers toward the cause, not just more alarms. The core lesson is that observability creates value when it drives decisions. Strong LLM dashboards connect reliability, tokens, cache behavior, routing, GPU health, cost, and quality. SLOs should mirror user experience. Alerts should target actionable symptoms, not noise. Next, we add version tracking, drift monitoring, cost attribution, and capstone architecture. What gets measured can be operated. What gets operated can be improved.